Close your eyes, breathe slowly. Let the darkness settle around you like something solid, like ground beneath your feet. Let the sounds of the present world, whatever small noises, reach you through the walls and the windows and the quiet of the night. Let them recede. Let them become the sounds of another time, or rather, let them become the sounds of no time at all, the sounds of before, because tonight we are going to a place that has never been a place in any human memory. We are going to a world so different from ours that the difference cannot be measured in the usual units, not in miles or degrees or years, but in the deep, slow language of the planet itself, in the language of continents moving and seas forming and mountains rising and life diverging across distances that did not yet exist. Tonight, we are going to imagine Pangea, not as it was not the actual Pangea of 250 million years ago, with its specific animals and its specific climate and its specific arrangement of rock and water, but as it might have been if it had never broken apart, if the forces that split the supercontinent had been slightly weaker, or the geology of the mantle slightly different, or the timing of the rifts slightly off, if the Atlantic Ocean had never opened, if South America and Africa had never separated, if India had never broken free and drifted northward to collide with Asia, if Antarctica had stayed connected to Australia and Australia had stayed connected to everything else, what would the world look like tonight if all the land were still one? If you could walk without crossing water from the place where you are lying to every other place on earth, if the oceans were one ocean, wrapping the single continent in a vast, unbroken embrace, that is what we are going to find out, slowly, quietly, in the way that the best questions are explored, not with urgency, not with anxiety, but with the patient, unhurried curiosity of someone who has nowhere to be and all night to get there. So let your body sink, let your thoughts soften, let the night hold you gently in the warmth and the dark, and let us go back past the dinosaurs, back past the first forests, back to the time when all the world was one, and then forward into the world that might have been if it had stayed that way, the continent that was one. There is a shape in the rock that tells the story. You can see it in any world atlas if you look at the outlines of the continents with the right kind of attention. South America fits against Africa like the pieces of a puzzle, not perfectly, not without gaps and overlaps, but closely enough to suggest that they were once together. The eastern coast of Brazil mirrors the western coast of the Gulf of Guinea. The bulge of West Africa slots into the indentation of the Caribbean coast of South America. The fit is not an illusion, not a coincidence, not a trick of cartographic projection. It is a memory written in the shape of coastlines that were once, a very long time ago, not coastlines at all. The German meteorologist Alfred Wegener noticed this fit in 1912 and proposed that the continents had once been joined in a single landmass that he called Pangea, from the Greek words for all and earth. He was not the first to notice the fit. The Flemish cartographer Abraham Ortelius had suggested the possibility in 1596, more than 3 centuries earlier, but he was the first to argue for it systematically, to gather geological and paleontological evidence in its support, to propose a mechanism and a timeline. The scientific community rejected him almost unanimously for decades. The idea that continents could move seemed absurd, his critics said, as suggesting that a continent could swim. He died in 1930 on a research expedition to Greenland, before the evidence that vindicated him had been assembled. By the 1960s, 1960s, the evidence was overwhelming. The discovery of seafloor spreading, the process by which new oceanic crust is continuously created at mid-ocean ridges and spreads outward, pushing the continents apart, provided the mechanism that Wegener had lacked. The magnetic patterns in the oceanic crust, which record the direction of the Earth's magnetic field at the time the rock solidified, confirmed the pattern of spreading with extraordinary precision. Plate tectonics became the foundational theory of geology, the grand unified framework within which everything about the Earth's surface, its earthquakes and volcanoes and mountains and ocean basins, and the distribution of its rocks and fossils, makes sense. And Pangea was confirmed. The supercontinent had existed. It had formed about 335 million years ago, when the collision of the older supercontinents, Gondwana and Laurussia, completed the assembly of all the world's major landmasses into a single body. It had lasted as a more or less complete entity until about 175 million years ago, when the first major rifts began to tear it apart. It had been the setting for the last great mass extinction, the Permian event of 252 million years ago. It had been the world that the first dinosaurs inherited, and it had, over the course of about 175 million years, broken into the world we know today. But it had been one for the better part of 160 million years, longer than the entire span. From the first dinosaurs to the present day, the Earth had been a single continent surrounded by a single ocean, and the world that existed on that supercontinent had been shaped in every detail by the fact of its unity. What Pangea actually was. Before we can imagine Pangea undivided, persisting into the present, we need to understand what the actual Pangea was like. Because the popular image of Pangea, a single blob of land surrounded by water, the kind of image you see on the covers of geology textbooks, is accurate in its outline, but impoverished in its detail. Pangea was not a flat, featureless lump of rock. It was a world of extraordinary topographic variety, of mountains and lowlands and river valleys and vast interior seas, of climate zones as different from each other as the modern tropics are from the modern poles. Pangea stretched from the South Pole to the North Pole. It was roughly centered on the equator, but it extended far into both hemispheres. Its shape was roughly triangular wide in the north, where the landmass of what is now North America, Europe, and Asia was broadest, narrowing toward the south, where the tip of what is now South Africa extended toward the Antarctic Circle. The supercontinent was asymmetric. Most of its mass was in the northern hemisphere, with the southern part, the Gondwana, half being somewhat narrower and more elongated. The interior of Pangea was vast. At the supercontinent's widest, you could have traveled from the western coast of what is now North America to the eastern coast of what is now China without crossing an ocean. A journey of perhaps 15,000 to 20,000 kilometers across, continuous land. No modern traveler can do anything comparable. Today, even the widest continuous landmass, the Eurasian continent, is bounded on east and west by oceans that require ships or aircraft to cross. Pangea was different. It was a world where, in principle, you could walk everywhere, where every species on land was connected by the medium of continuous habitat to every other species on land. The climate of Pangea was determined primarily by this geometry. The interior of the supercontinent, far from any ocean, cut off from the moisture-bearing winds that the oceans generate, was arid, extraordinarily arid, interior desert of Pangea was larger than any desert on the modern Earth. The modern Sahara, the largest hot desert in the world, covers about 9.2 million square kilometers. The interior desert of Pangea may have covered 30 to 40 million square kilometers, an area larger than North America and Europe combined. It was the driest place on a planet, a place where rain fell perhaps once in a decade, where the temperature swings between day and night were enormous, where the rock was bare and red and sculpted by wind rather than water. The coasts of Pangea were wetter. The ocean, the Panthalassa, the great world ocean that surrounded the supercontinent, delivered moisture to the coastal regions, and the seasonal monsoons that the ocean continent temperature contrast generated brought rainfall to the coastal lowlands. The coastal regions of Pangea, particularly those in the equatorial zone, were not deserts. They were forested, sometimes densely, with the conifers and seed ferns and cycads of the Permian and the Triassic. But between the wet coasts and the arid interior was an enormous zone of transition, semi-arid landscapes, dry woodlands, scrublands, grasslands, of primitive grasses that had not yet fully diversified. This transition zone was vast because the distances involved were vast. In a continent as large as Pangea, the gradient from coast to interior was stretched across thousands of kilometers, producing climate zones of continental scale. The northern part of Pangea, roughly equivalent to the modern landmasses of North America, Europe, and Asia, was called Laurasia. The southern part, roughly equivalent to South America, Africa, the Indian subcontinent, Antarctica, and Australia, was called Gondwana. The two halves had come together to form Pangea, and their geological histories were somewhat different. Laurasia was generally lower-lying, with more of its area covered by shallow inland seas. Gondwana was higher and more elevated, with the remnants of ancient mountain ranges from previous collisions still present on its surface. Between Laurasia and Gondwana, on the eastern side of Pangea, was the Tethys Sea, a vast, warm, shallow embayment of the Panthalassa that cut deeply into the eastern side of the supercontinent. The Tethys was not an ocean in the full sense. It was more like an enormous bay, hundreds of thousands of square kilometers in area, warm and biologically productive, its shallow shelves rich in marine life. It was the Mediterranean of its time, but far larger. And it was the reason why the eastern coast of Pangea was wetter and more biologically productive than the western coast. The forces that broke it apart, and what if they hadn't? Pangea broke apart because of the same forces that assembled it. Plate tectonics, the slow, relentless movement of the lithospheric plates driven by convection in the mantle beneath. The heat of the Earth's interior, generated by the decay of radioactive elements and by the residual heat of the planet's formation, drives the mantle to convect, to circulate slowly over millions of years in enormous cells of rising and falling rock. Where mantle material rises to the surface, it creates divergent boundaries, places where the crust is pulled apart, where new ocean floor is created, where continents can be rifted and separated. The specific rifting of Pangea was triggered by the accumulation of heat beneath the supercontinent. A supercontinent acts as an insulating blanket over the mantle beneath it. The heat that would normally be radiated away from the oceanic floor is trapped beneath the thick, buoyant continental crust. Over millions of years, this trapped heat builds up, creating anomalously hot regions beneath the continent. Eventually, the heat becomes sufficient to melt the overlying crust from below, to push it upward, to create rifts, long, linear fractures in the crust, along which the continent begins to split. The first major rift in Pangea opened around 175 million years ago in the early Jurassic. It separated the northern part of Pangea Laurasia from the southern part Gondwana, creating the embryonic Tethys Ocean. This rift was followed, over the next tens of millions of years, by additional rifts that progressively fragmented the supercontinent. The Central Atlantic opened, separating North America from Africa. The South Atlantic opened, separating South America from Africa. India detached from Antarctica and began its long northward drift. Antarctica separated from Australia. The North Atlantic opened, separating Europe from North America. Each of these rifts was driven by the same basic mechanism: mantle heat accumulating beneath the supercontinent, creating a bulge in the crust, which then domed upward and fractured along linear zones of weakness, which were then invaded by basaltic magma that cooled to form new oceanic crust as the continents drifted apart. The process was slow centimeters per year, the same speed at which your fingernails grow, but over tens of millions of years, it produced the oceans and the separated continents of the modern world. Now imagine that this process was slightly different, not radically different. The mantle would still convect, the heat would still accumulate, the crust would still experience stress. But imagine that the specific geometry of the convection cells beneath Pangea was such that the upwelling zones were smaller or less focused, or located in positions where they produced less effective rifting. Imagine that the mantle plumes the columns of hot rock that are associated with the most intense volcanic episodes, and the most powerful rifting events were slightly weaker or positioned slightly differently, or that the continental crust of Pangea was slightly thicker and more resistant to rifting. In this scenario, Pangea does not break apart, or it breaks apart incompletely. Small rifts open, but do not propagate to full rifting, do not produce new ocean floor, do not separate the continents. Narrow seas form shallow, warm, inland seas, similar to the Tethys, but not connecting to the full open ocean, and then close again as the rifting fails. The supercontinent holds together. It deforms, it is compressed in some places, stretched in others, its surface reshaped by the continuing activity of the mantle beneath it, but it remains one. And tonight, we stand on that continent. 200 million years have passed. The Jurassic has come and gone, without the fragmentation of the continents. The Cretaceous has come and gone. The great extinctions have happened perhaps differently than in our world, because the geography that shaped them is different, but life has persisted and diversified. We are in the present, in a world where Pangea never broke apart, looking out at a landscape and a world that no human eye has ever actually seen, the climate of the eternal supercontinent. The single most dramatic consequence of Pangea's survival would be its climate, and the climate of a world with a single supercontinent would be so different from what we know that the word climate barely captures the gulf between the two worlds. In the modern world, the climate is moderated by the oceans. The oceans cover 71% of the Earth's surface. They absorb heat in summer and release it in winter. They carry warm water from the equator toward the poles in great currents, the Gulf Stream, the Kuroshio, the various limbs of the global thermohaline circulation, moderating the temperatures of the high latitudes. They evaporate water, which becomes rain over the land. They are, in short, the great regulator of the Earth's climate, the buffer that keeps temperatures from swinging to the extremes that a pure land surface would produce. In the world of Pangea undivided, the ocean would still cover most of the planet's surface. The Panthalassa, the world ocean, would be even larger than today's combined oceans, covering the entire hemisphere opposite the supercontinent. But the critical difference is that this ocean would be very far from most of the land. The interior of Pangea, which would still be vast, perhaps even larger and more interior dominated than the original Pangea, after 200 million more years of the continent's existence, would be cut off from oceanic influence by thousands of kilometers of intervening land. The seasonal temperature swings of the Pangean interior would be extreme beyond anything experienced on the modern Earth. In summer, when the sun is high and the days are long, the interior of the supercontinent would absorb enormous amounts of solar energy. Without the moderating influence of nearby oceans, the temperature would rise dramatically, perhaps to 55 or 60 degrees Celsius in the hottest regions, comparable to the surface temperature of a car left in direct sunlight. In winter, with no oceanic heat to moderate the cold, the temperatures in the interior would plummet perhaps to -40 or -50 degrees Celsius, comparable to the coldest modern continental interiors like Siberia or the high plains of Canada, but even more extreme. These extremes would produce an interior that oscillates between scorching summer heat and brutal winter cold, with no temperate zone between. The plants and animals of the interior would need to survive both extremes, which severely restricts the range of possible life forms. Only the hardiest, most physiologically flexible organisms could survive in the deep interior of Pangea undivided. Most life would be concentrated near the coasts. The monsoon systems of Pangea undivided would be the largest and most powerful monsoons in the history of the planet. The principle of the monsoon is simple. Land heats up and cools down faster than ocean water. In summer, the land becomes hotter than the ocean, and the hot air over the land rises, drawing in moist air from the ocean to replace it. This moist oceanic air brings rainfall to the coastal regions. In winter, the process reverses. The land cools faster than the ocean. Cold air sinks over the land and flows outward, pushing the moist oceanic air back to sea. In the modern world, the largest monsoon systems, the South Asian monsoon, the East Asian monsoon, the West African monsoon, the North Australian monsoon, are impressive and life-giving. They bring the seasonal rainfall that makes large areas of Asia and Africa and Australia productive enough to support billions of people. But they are limited in scale by the fact that the modern continents are not very large compared to the oceans, and by the fact that the oceans surround the continents on multiple sides, limiting the distance over which the monsoon can penetrate inland. In Pangea undivided, the monsoon would be continental in scale. The temperature contrast between the supercontinent and the surrounding ocean would be enormous, far larger than any modern land-ocean contrast, and the monsoon circulation it drove would be correspondingly powerful. In summer, the monsoon winds would blow strongly onshore from the Panthalassa, carrying enormous quantities of moisture that would fall as rain on the coastal regions of the supercontinent. The coastal monsoon rainfall in Pangea undivided would be spectacular, perhaps twice or 3 times the rainfall of the modern South Asian monsoon at its peak. Coastal areas would receive vast amounts of rain in a short season, the land flooded periodically, the rivers raging, the vegetation lush and dense during the wet season, and then the dry season would arrive. The monsoon would reverse. The cold, dry air of the interior would flow outward toward the coast, pushing the moisture back to sea. The rivers would fall to a trickle. The vegetation would dry. The lakes would shrink. The fires would come. This alternation between a violent wet season and a prolonged, brutal dry season would shape the ecology of the coastal zones more profoundly than any feature of the modern world's climate does. The poles of Pangea undivided would be complicated. In the actual Pangea, the southern polar region, Antarctica, was glaciated at various times, and the northern polar region experienced varying degrees of cold. In Pangea undivided, whether the poles were glaciated would depend on the specific atmospheric CO2 concentration and the Earth's orbital parameters, the same Milankovitch cycles that drive our own ice ages. If CO2 levels were similar to modern levels, the polar regions of Pangea undivided would likely be cold, possibly with ice caps. If CO2 were higher, as it has been for most of Earth's history, the poles would be warmer, perhaps ice-free, covered in cold-adapted forests or tundra. The global climate of Pangea undivided would be a climate of extremes: extreme heat in the interior, extreme rainfall on the coasts, extreme cold at the poles, if glaciated, and extreme seasonality everywhere. There would be no place on the supercontinent with the mild, moderate, year-round climate that we associate with the most productive and hospitable regions of the modern world. The Mediterranean climate of California or Southern Europe, the temperate oceanic climate of Western Europe, the humid subtropical climate of the Eastern United States or Eastern China. Those climates require a particular configuration of ocean and land that does not exist in the world of Pangea undivided, the ocean that would have swallowed the world. The Panthalassa, the name means all sea, a perfect mirror of Pangea, would be the most extraordinary feature of the world of Pangea undivided. It would cover the entire hemisphere opposite the supercontinent. Its width, measured along the equator, would be approximately 20,000 kilometers, roughly half the circumference of the Earth. No modern ocean comes close. The Pacific Ocean, the largest modern ocean, is about 19,800 kilometers wide at its widest, but the Pacific does not cover a full hemisphere. It is flanked by the Americas on the east and Asia and Australia on the west. The Panthalassa would have no such flanking. It would be an unbroken expanse of water from the eastern coast of Pangea westward, all the way around to the western coast of Pangea, a true world ocean wrapping the planet in a single, connected mass of water. The Panthalassa would be the largest single body of water in the history of the planet, not just of the Cenozoic or the Mesozoic, but in the entire 4-5 billion year history of the Earth. Its area would be approximately 350 million square kilometers compared to the combined area of all modern oceans, which is about 361 million square kilometers. Wait, that is almost the same. The reason is that the Panthalassa, though wider, would not be deeper or shallower on average than modern oceans, and the total water on Earth is fixed. The Panthalassa and the modern oceans together would have essentially the same total volume of water, but the distribution of that water would be radically different. Instead of several separate basins, the Atlantic, the Pacific, the Indian, the Arctic, all connected at their margins, there would be one enormous basin, connected everywhere to itself. This would have profound consequences for ocean circulation, the modern ocean circulation, the thermohaline circulation. The great conveyor belt of ocean water works by moving cold, dense water from the high latitudes to the deep ocean, and then moving it slowly around the globe, eventually bringing it back to the surface in upwelling zones. This circulation is shaped by the geometry of the ocean basins, the configuration of the continents, the locations of the narrow straits that connect or separate basins, the distribution of the continental shelves. In the modern world, the critical choke points of ocean circulation, the Drake Passage between South America and Antarctica, the Strait of Gibraltar, the Indonesian throughflow, play outsized roles in determining how water moves around the planet. In the Panthalassa, there would be no such choke points. The ocean would be free to circulate without restriction. The dominant pattern of circulation would be driven by the trade winds, the steady equatorial winds that blow from east to west in the tropics, which would drive a massive equatorial current around the entire circumference of the Panthalassa. This equatorial current, circling the globe without interruption, would be perhaps the most powerful ocean current in the history of the planet. It would carry enormous quantities of warm tropical water westward, heating the western margin of the ocean, the eastern coast of Pangea, and cooling the eastern margin, the western coast of Pangea. The Panthalassa would also have enormous gyres, circular systems of ocean currents that fill the mid-latitude regions of the ocean basins. In the modern Pacific, there is the North Pacific Gyre and the South Pacific Gyre, each thousands of kilometers across. In the Panthalassa, the gyres would be even larger, potentially spanning entire hemispheres, carrying water from the tropics to the mid-latitudes and back again in lazy, enormous spirals. The productivity of the Panthalassa would depend on its upwelling systems, upwelling where cold, nutrient-rich water from the deep ocean rises to the surface, is the engine of the most productive marine ecosystems. In the modern world, the major upwelling systems are found along the eastern margins of the ocean basins, where the trade winds push surface water offshore and deeper water rises to replace it. In the Panthalassa, the upwelling system along the western coast of Pangea, the eastern margin of the world ocean, would be enormous, perhaps the most productive marine ecosystem in the history of the planet. Cold, nutrient-rich water rising continuously along thousands of kilometers of coastline, supporting vast populations of fish and marine mammals and seabirds. The storms of the Panthalassa would also be extreme. The trade winds and the seasonal monsoons would generate large waves that would have enormous fetches the distance over which the wind blows across the water surface, which determines the height of the waves. In the modern Pacific, the fetch of the trade winds is already impressive, generating swells that travel thousands of kilometers before reaching shore. In the Panthalassa, the fetch would be even greater. The winds could blow uninterrupted across the entire equatorial circumference of the planet, generating swells of extraordinary scale that would reach the coasts of Pangea as enormous waves. The coastlines of Pangea, undivided, would be shaped by these waves. The western coast, facing into the prevailing westerly winds of the mid-latitudes, would be exposed to powerful surf. The eastern coast, on the sheltered side of the supercontinent, would be calmer. The monsoon coasts would alternate between seasons of powerful storm surf and seasons of relative calm. The entire coastal zone of Pangea would be a place of dynamic interaction between land and the world ocean, shaped by forces that dwarf anything in the modern world. The desert, at the heart of everything, at the center of Pangea, undivided, there would be a desert, not a desert like the Sahara, not a desert like the Gobi, not even a desert like the Rub al-Khali, the empty quarter of the Arabian Peninsula. Those are large deserts, impressive deserts, deserts that challenge the human imagination. But the desert at the heart of Pangea, undivided, would dwarf all of them combined. It would cover perhaps 40 or 50 million square kilometers. To put that in perspective, the entire continent of Africa is about 30 million square kilometers. The interior desert of Pangea undivided would be larger than Africa and Europe combined, larger than North and South America combined, larger than any geographical feature in the modern world that is not an ocean. It would stretch from approximately 20 degrees north of the equator to 20 degrees south, and from the interior of what would be the eastern part of the continent to the interior of the western part, a span of perhaps 12,000 kilometers from east to west, 5,000 or 6,000 kilometers from north to south. This desert would be extraordinarily hot. The equatorial latitudes receive the most direct solar radiation of any region on Earth, and without the cooling effect of nearby oceans, the surface temperature of the desert interior would be extreme. During the summer months, surface temperatures could reach 70 or 75 degrees Celsius, hotter than the surface of the Sahara on its hottest days, hotter than any place on the modern Earth at the land surface. The air temperature, a meter above the ground, would reach 55 to 60 degrees Celsius. No modern animal larger than a beetle could survive these temperatures for long. The desert would also be extraordinarily dry. The interior of Pangea, undivided, would receive perhaps a few millimeters of precipitation per year, not per month, per year. For comparison, the driest parts of the Atacama Desert in South America, the driest desert in the modern world, receive about 1 to 3 millimeters per year. The interior of Pangea undivided would be comparable to the driest parts of the Atacama, but on an incomparably larger scale and at much higher temperatures. The combination of heat and aridity would make the deep interior of the supercontinent essentially lifeless, not a thriving but sparse desert ecosystem, like the modern Sahara with its scattered oases and its populations of camels and gazelles and humans, but a true dead zone, a landscape as devoid of macroscopic life as the surface of Mars. The rocks of this interior desert would be shaped primarily by wind and thermal expansion and contraction. Water erosion, the dominant process that shapes landscapes in wetter climates, would be essentially absent. Instead, the temperature swings between the scorching days and the cold nights would cause the rock to expand and contract repeatedly, cracking along mineral boundaries, spalling off flakes of rock that would then be picked up by the wind and carried sometimes hundreds of kilometers before being deposited as sand dunes or loess deposits. The dune fields of the interior would be immense, larger than any modern dune field, potentially covering millions of square kilometers in graceful, wind-sculpted forms. Seif dunes and Barchan dunes and star dunes, their shapes determined by the prevailing wind patterns, advancing slowly across the desert floor. The dust storms of the interior desert would be continental in scale. When the seasonal temperature gradients shifted in the transition between the summer and winter hemispheres, when the pressure systems over the continent reorganized, the resulting winds would pick up enormous quantities of fine dust and carry it high into the atmosphere. These dust events would darken the sky over the desert, sometimes for weeks at a time, the sun reduced to a pale disk behind a wall of suspended rock flour. The dust would be carried by upper-level winds to the coastal regions, where it would fall as a reddish haze, coating the vegetation with a fine mineral powder. The edges of the desert, the transition zones between the dead interior and the living coasts, would be among the most dynamic landscapes on Pangea undivided. These zones would be not just dry but seasonally variable. In the wet season, when the monsoon pushed moisture inland from the coasts, the edge of the desert would receive enough rain to support a sparse but real vegetation, drought-adapted plants, deep-rooted shrubs, succulent plants, that could store water through the long, dry season. In the dry season, these plants would be dormant or leafless, the soil cracked, the rivers dry. Animals would follow the seasonal rains, migrating inland during the wet season to exploit the brief bounty, retreating to the permanent water sources of the coast during the dry season, the mountains that would have scraped the sky. In the world of Pangea undivided, the mountains would be different from any mountains on the modern earth, not because the basic physics of mountain building, the collision of tectonic plates, the folding and thickening of the crust would be different, but because the specific collisions that produced the mountains would be different, and because the mountains would have had 200 million more years to evolve, to be eroded, to be re-uplifted, and to interact with the climate in ways that no modern mountain range has had time for. In our world, some of the great mountain ranges are the result of continental collisions that followed the breakup of Pangea. The Himalayas, the highest mountains on Earth, the home of Everest and K2, and the other great peaks that define our image of mountain grandeur, are the result of the collision of India with Asia, a collision that began about 50 million years ago and is still continuing. In the world of Pangea undivided, this collision would never have happened because India would never have separated from Gondwana, would never have drifted northward across the ancient Tethys, would never have slammed into Asia with the force that built the Himalayas. There would be no Himalayas in the world of Pangea undivided, but there would be other mountains. The forces that would have acted on Pangea undivided over 200 million years would not have been entirely quiescent. Even without the rifting that broke the supercontinent apart, there would have been subduction, the process by which dense oceanic crust descends beneath the lighter continental crust at convergent boundaries along the margins of the Panthalassa. The oceanic crust of the Panthalassa, moving under the influence of mantle convection, would have descended beneath the edges of Pangea, driving volcanic arcs and mountain building along the coasts. These coastal mountain ranges, the Pangean equivalent of the modern Andes and the Cascades, and the mountains of Japan, would have grown and eroded and grown again over hundreds of millions of years. The interior of Pangea undivided would also have experienced significant mountain building, driven by the compression generated by the subduction along the coasts. The crust of the interior, compressed from the margins, would buckle and thicken, producing broad upland plateaus and mountain ranges somewhat like the modern Tibetan Plateau, but perhaps even larger, because the compression from a surrounding ocean acting on all sides of the supercontinent would be more symmetric and more sustained than the compression that produced the Tibetan Plateau. These interior plateaus would be high, perhaps 4 or 5 kilometers above sea level on average, with individual peaks reaching 7 or 8 kilometers. At those altitudes, even in the hot climate of the lower latitudes, the temperatures would be cold enough for permanent ice. The high plateaus of the interior would bear glaciers, not the valley glaciers of the modern temperate mountains, but the broad, flat ice fields of the high polar plateau type, spreading across the elevated surface and sending outlet glaciers down the mountain flanks toward the lower ground. The interaction between these interior mountains and the desert that surrounded them would be extraordinary. The mountains would force the monsoon winds upward, causing them to drop their moisture on the mountain flanks before they could penetrate to the interior. The result would be sharp precipitation gradients, the windward sides of the mountains receiving enormous rainfall, the lee sides in deep rain shadow. The difference between the two sides, sometimes amounting to several meters of rainfall per year, over a horizontal distance of a few hundred kilometers. The rivers draining the wet windward slopes would be powerful and erosive, cutting deep gorges into the mountain flanks. The rivers draining the dry lee slopes would be thin and ephemeral, barely reaching the desert floor before evaporating. The highest mountains of Pangea, undivided, the great peaks of the subduction-driven coastal ranges, might rival or exceed the modern Himalayas in absolute height. The Andes, at their highest, reach about 6,961 meters. The Himalayas reach 8,849 meters. A coastal subduction range that had been building and being re-energized by continuous subduction for 200 million years might produce peaks of 9,000 or even 10,000 meters, pushing against the theoretical upper limit of what a mountain can be before its own weight causes the rock beneath it to flow and the peak to collapse. At these extreme altitudes, the peaks would protrude into the lower stratosphere. The weather at those altitudes would be uniquely violent jet streams. The powerful high-altitude winds that circle the Earth in the upper troposphere would interact with the peaks, generating ferocious downslope winds on the lee sides, creating complex patterns of turbulence and wave clouds that would be visible from enormous distances. The peaks themselves would be permanently enveloped in ice and snow, their upper flanks too cold and too windswept for any life, their lower flanks the home of cold-adapted specialists. The rivers of Pangea undivided. The rivers of Pangea undivided would be among the most spectacular features of that world. A river's character, its size, its behavior, its relationship to the landscape is determined by the size and topography of its drainage basin and by the precipitation that falls within that basin. In the world of Pangea undivided, both of these factors would be extreme. The largest rivers of Pangea undivided would drain basins of continental-scale catchment areas that would dwarf the drainage basins of any modern river. The Amazon, the largest river in the modern world, by discharge, drains about 7 million square kilometers. The Congo, the second largest by discharge, drains about 3.7 million square kilometers. The rivers of Pangea undivided, draining the enormous landmass of the supercontinent, might have drainage basins of 15 or 20 or even 30 million square kilometers, 2 to 4 times the size of the Amazon basin. These rivers would collect the runoff from the monsoon rains that fell on the coastal regions of the supercontinent and carry it toward the interior. But here they would face a challenge. The interior of Pangea undivided is a desert. The rivers would be fighting against evaporation, against the permeable desert sands, against the immense dryness of the interior. Most of them would not make it to the far side of the continent. They would progressively lose water to evaporation and seepage as they crossed the desert, becoming smaller and smaller, eventually disappearing into the sand. The rivers that managed to cross the desert, perhaps those that followed topographic channels where the water table was high, where the bedrock was close to the surface and impermeable, where the depth of the channel provided some shelter from the worst of the evaporation, would be extraordinary. They would be slow, wide, heavily loaded with sediment picked up from the desert they had crossed. Their channels would be complex, braided systems of multiple threads weaving between sandbars, their banks unstable, their beds constantly shifting. Where they finally reached the opposite coast, they would deposit their sediment in enormous deltas, vast areas of flat, waterlogged land built up over millions of years from the material washed off the continental interior. The rivers draining the high interior plateaus toward the coast would be different, steep, swift, and powerful, cutting deep gorges through the mountain rocks, carrying enormous loads of coarse sediment. Where these rivers emerged from the mountain fronts onto the lower coastal plain, they would spread out in broad alluvial fans, depositing their coarse load in spreading sheets of gravel and sand. In the wet season, these alluvial fans would be flooded the rivers, spreading across the fan surface in braided sheets of water and sediment. In the dry season, the water would retreat into the channel, leaving the fans dry and dusty. The largest permanent rivers of Pangea undivided would have mouths of extraordinary size. Where a river carrying the drainage of a basin the size of the modern Amazon debouches into the Panthalassa, it would create a plume of fresh water, sediment, and dissolved nutrients that would extend hundreds of kilometers into the ocean. The biological productivity of the ocean around these river mouths would be exceptional. The nutrients from the continental interior, concentrated over millions of square kilometers of drainage basin, would fertilize a bloom of phytoplankton and support a rich food web of zooplankton, fish, marine mammals, and seabirds. Some rivers of Pangea undivided would end not in the ocean, but in interior basins, closed drainage systems, where the river flows into a lake or a salt flat and has no outlet to the sea. In the arid interior of the supercontinent, such interior drainage would be common. The lake or salt flat at the center of an interior drainage basin would accumulate the dissolved minerals carried by the rivers, becoming increasingly saline over time. Some of these interior seas would be vast, comparable in area to the modern Caspian Sea, which is itself the largest interior body of water on Earth, or perhaps even larger. They would be hypersaline, their shores encrusted with salt, their waters supporting only the most salt-tolerant organisms: brine shrimp, halophytic bacteria, the specialized plants that can tolerate high salt concentrations in their tissues. The life that would have stayed connected, the most profound biological consequence of Pangea never breaking apart, would be the consequences for evolution itself. The breakup of Pangea is not just a geographical event in our world's history. It is one of the most important events in the history of life, because it separated populations of organisms that had previously been connected, creating the geographic isolation that is the engine of speciation and the ultimate source of biological diversity. When a population of organisms is separated by a geographical barrier, an ocean, a mountain range, a desert, it can no longer interbreed with the populations on the other side of the barrier. The two separated populations, subject to different environments and different selective pressures, evolve in different directions. Over time, thousands of years for rapidly reproducing organisms, millions of years for slowly reproducing ones, the two populations become genetically distinct. They become separate species. This process, called allopatric speciation, is the primary mechanism by which new species are created, and it has been the dominant driver of biodiversity throughout the history of life. The breakup of Pangea was perhaps the greatest speciation event in the history of land life. When South America separated from Africa, populations of animals and plants that had been connected became isolated. They evolved separately for tens of millions of years, producing the extraordinary differences between the fauna and flora of the New World and the Old World that still characterize our world today. When India separated from Gondwana and drifted northward, its populations of organisms were isolated for 65 million years before India's collision with Asia allowed species to mix again. And during those 65 million years, India's isolated fauna and flora evolved in their own direction, producing lineages found nowhere else on Earth. When Australia separated from Antarctica, it became the most biologically isolated continent on the planet, its marsupials and monotremes evolving for 45 million years without contact with the placental mammals. that came to dominate the rest of the world. In the world of Pangea undivided, none of this would have happened. The populations of organisms on the supercontinent would have remained connected, not necessarily in constant genetic contact, because the desert interior would have been an effective barrier to many organisms, and the mountains, and the rivers, and the climate zones would have created local isolation for shorter periods, but connected enough that genetic exchange would have been possible on geological timescales, connected enough that a new species evolving in one part of the supercontinent could, over millions of years, spread to other parts if it was successful enough. This connectivity would have profound consequences for biodiversity. In the modern world, the separation of the continents has produced multiple independent solutions to the same ecological challenges, multiple independent evolutions of large herbivores, of apex predators, of burrowing insectivores, of flying organisms, of aquatic specialists. Africa has elephants, South America has tapirs, Australia has wombats, all filling roughly similar ecological roles, but produced by completely independent evolutionary lineages. This redundancy, the same ecological function being performed by unrelated organisms in different parts of the world, is a consequence of geographic isolation. In Pangea undivided, this redundancy would be less extreme. A successful large herbivore evolving in one part of the supercontinent could spread to fill the corresponding ecological role in other parts, preventing or delaying the independent evolution of a different large herbivore elsewhere. The ecological niches of Pangea undivided would tend to be filled by single, widespread lineages rather than by multiple, independent lineages in different regions. The world would be biologically less diverse, fewer species overall, because the geographic isolation that generates new species would be less pervasive, but the species that existed would tend to have much larger geographic ranges because nothing would prevent them from spreading. The difference in total biodiversity between the modern world and the world of Pangea undivided would be enormous. The modern Earth supports an estimated 8 to 10 million species, of which only about 1.5 million have been formally described. Much of this diversity is the direct result of the geographic isolation that followed the breakup of Pangea and the evolution of separate biotas on separate continents. In Pangea undivided, the total number of species would probably be much lower, perhaps 2 to 4 million, or even fewer. But the species that did exist would be more cosmopolitan, more widespread, and in some cases, more ecologically dominant than any species in the modern world, the animals that would never have diverged. Let us think specifically about the animals, the vertebrates, particularly of the world of Pangea undivided. What would the large animals of this world look like after 200 million years of evolution on a connected supercontinent? The dinosaurs, or rather, their descendants, in our world, the non-avian dinosaurs went extinct 66 million years ago, the victims of the Chicxulub impact and the associated environmental catastrophe. In the world of Pangea undivided, this extinction event might have been slightly different. The geography of the impact and the geography of the world it struck would be different, and the pattern of extinction might have been different as well. But let us assume, for the sake of this exploration, that the impact happened and that the non-avian dinosaurs went extinct much as they did in our world. The birds, the avian dinosaurs, the one lineage of dinosaurs that survived the extinction, would still be present in the world of Pangea undivided. The birds of Pangea undivided would have had 66 million years to diversify and fill the ecological niches available on the supercontinent. In our world, birds have diversified into approximately 10,000 species, occupying a vast range of ecological niches, from the smallest hummingbirds to the largest ostriches, from the deep-sea diving penguins to the high-altitude geese. On Pangea undivided, the bird fauna would be different in its specific species, but perhaps comparable in its ecological range. The mammals of Pangea undivided would be the most fascinating aspect of the world's fauna. In our world, the separation of the continents produced the extraordinary divergence between the placental mammals, which dominate most of the world, and the marsupial mammals, which dominate Australia and were previously found in South America. This divergence is the result of geographic isolation. When South America and Australia were cut off from the rest of the world, the marsupials that were present at the time of separation continued to diversify in isolation, eventually producing the kangaroos and koalas and wombats and possums and Tasmanian devils that we know today. The placental mammals, evolving on the larger connected land masses, were generally more successful in ecological competition and spread wherever the continents were connected. In Pangea undivided, there would be no marsupial-dominated continents, because there would be no isolated continents. The marsupials and placentals would have competed with each other on the same continuous landmass for the entire 66 million years since the extinction of the non-avian dinosaurs. In our world, the evidence suggests that placentals are generally more competitive than marsupials in head-to-head ecological competition wherever the continents have connected and the two groups have met. Placentals have generally prevailed. In the world of Pangea undivided, this competition would have played out over the entire supercontinent, and the likely outcome would be the dominance of placentals, with marsupials either extinct or surviving in marginal habitats. The specific lineages of placentals that dominated Pangea undivided would depend on the specific history of 66 million years of evolution on the supercontinent, a history we cannot fully predict. But some things are likely. The large herbivores would almost certainly be very different from the combination of elephants, rhinoceroses, hippos, horses, cattle, deer, and camels that fill large herbivore niches in the modern world. In Pangea undivided, the large herbivore niche would be filled by whichever lineage was most successful in the particular ecological conditions of the supercontinent, likely something adapted to the extreme seasonality of the monsoon climate, capable of migrating long distances between wet and dry seasons, capable of surviving on sparse and tough vegetation during the dry months. The apex predators of Pangea undivided would be similarly different from what we know. The cats and dogs and bears of the modern world are all products of specific evolutionary histories shaped by continental separation. In Pangea undivided, the apex predator niche might be filled by a completely different lineage, one that had outcompeted all others on the connected supercontinent over millions of years, becoming the single dominant predator across all of Pangea, rather than the multiple independent lineages of cats, dogs, and bears that we know. The diversity of insects on Pangea undivided would be substantially lower than in the modern world. Insects are the most species-rich group of organisms on Earth. The beetles alone are estimated to include more than 400,000 species, and much of their diversity is the result of coevolution with flowering plants and with the geographic isolation that allowed independent evolutionary radiations on separated land masses. In Pangea undivided, the insects would still be diverse, probably the most species-rich group of animals, as they are today, but less so than in our world. The birds of coasts and the open ocean of the Panthalassa would be a rich and interesting fauna. Seabirds in our world have evolved on multiple continents and islands, producing a diverse range of forms: albatrosses and petrels and shearwaters and storm petrels, gannets and boobies and frigate birds, gulls and terns and skuas, penguins and auks and puffins. In the world of Pangea undivided, the seabird fauna would be shaped by the single coastline and the vast Panthalassa. The ecological roles would be similar: long-range ocean foragers, coastal plunge divers, surface feeders, plunge divers, but the specific lineages filling them would reflect the specific evolutionary history of birds on the undivided supercontinent, the creatures that would have grown immense. One of the most intriguing possibilities of the world of Pangea undivided is the potential for the evolution of organisms of extreme-size creatures, larger than anything in the modern world, exploiting the vast, continuous habitats of the supercontinent. Body size in animals is constrained by many factors: available food, metabolic efficiency, structural limits of bone and muscle, the energy costs of thermoregulation, the availability of water, competition with other species. But one factor that is often underappreciated is habitat continuity. Large animals require large habitats. A species that grows very large needs a habitat large enough to sustain a viable population, enough individuals to maintain genetic diversity, enough food to sustain those individuals. In the fragmented world of modern continents, the maximum practical size of a land animal is limited by the size of the largest continuous habitat. In Pangea undivided, the continuous habitats would be enormous. The mammoth steppe of the Pleistocene, an area of about 20 million square kilometers, sustained the woolly mammoth, the largest land animal of the recent past, at perhaps 3 to 4 meters at the shoulder. The coastal grasslands and savannas of Pangea undivided might cover 100 million square kilometers or more of productive habitat in such vast continuous landscapes. The evolutionary pressure toward larger size, which can confer advantages in both competitive interactions and in surviving periods of food scarcity, might produce animals significantly larger than any modern land animal. The largest land animal in the modern world is the African elephant, at about 4 meters at the shoulder and up to 7 tons. The largest land animals in the history of life were the sauropod dinosaurs, titanosaurs, like Patagotitan and Argentinosaurus, which may have reached 25 to 30 meters in length and 50 to 70 tons. These were products of the Mesozoic, a world very different from ours, but they demonstrate that the theoretical upper limit of land animal size is far above what the modern world has actually produced. In the world of Pangea undivided, given 200 million years of evolution on a connected supercontinent with vast continuous habitats, it is not unreasonable to imagine land animals significantly larger than the modern elephant. Not as large as the sauropods, the ecological conditions of the modern era are different from those of the Jurassic, but perhaps animals of 8 or 10 or 12 tons, browsers or grazers of the coastal plains and the edge zones of the interior. These would be creatures unlike anything we know, not mammoths, not rhinoceroses, not elephants, something new, shaped by 200 million years of evolution that did not happen in our world, filling the ecological role of the large herbivore in a world without the geographic barriers that fractured that role into dozens of separate lineages in our own world. The large predators of Pangea, undivided, might also be extreme. A predator capable of hunting prey animals of 8 to 12 tons would need to be large itself, perhaps comparable to the largest carnivores in the fossil record, the great bear dogs, and the largest of the saber-toothed cats, but potentially larger. Or perhaps the apex predators of Pangea, undivided, would not be individual large animals at all, but highly organized pack hunters, the large-scale equivalent of wolf packs or lion prides, whose collective hunting strategy, rather than individual size, allowed them to bring down the giant herbivores. The birds of Pangea, undivided, might also reach extreme sizes in certain ecological contexts. The largest modern birds are the ostriches and emus and cassowaries, flightless birds of the continental interiors. In Pangea, undivided, without the geographic isolation that produced the multiple independent lineages of large flightless birds in our world, there might be a single dominant lineage of giant terrestrial birds, evolving over millions of years into forms that dwarf any modern bird. Or there might be no giant flightless birds at all if the competition from large mammals prevented the ecological conditions that allow giant flightless birds to thrive. The seas at the edge of the world. The Tethys Sea of the actual Pangea was a remarkable body of water, warm, shallow, biologically rich, the birthplace of many marine lineages that would later spread to dominate the world ocean. In the world of Pangea, undivided, the Tethys, or something like it, might still exist, a shallow, epicontinental sea, or a series of such seas, occupying low-lying regions of the supercontinent's interior or margins. Shallow epicontinental seas that flood low-lying continental areas, were a common feature of Earth's past. During much of the Cretaceous, a shallow sea called the Western Interior Seaway divided North America from north to south, creating an inland sea teeming with marine reptiles and ammonoids. Similar seas have existed over much of geological time, flooding the low areas of continental platforms when sea level was high relative to the land. In Pangea, undivided, after 200 million years of geological activity, there would almost certainly be regions of the supercontinent where the land surface was below or near sea level areas that had subsided due to the weight of sediment or due to the stretching of the crust in regions where the underlying mantle had thinned. These low-lying areas would be flooded by the Panthalassa, creating a series of shallow inland seas at the margins of the supercontinent. These inland seas would be some of the most biologically productive environments on Pangea, undivided. Shallow marine environments, continental shelves, and inland seas receive abundant sunlight and are rich in nutrients from both terrestrial runoff and from the mixing of shallow and deep water. They support diverse communities of marine invertebrates, fish, marine reptiles, or their evolutionary descendants, and marine mammals. In the world of Pangea, undivided, these inland seas would be connected to the Panthalassa, allowing marine species to colonize them from the open ocean, and they would provide sheltered environments for the evolution of specialized coastal and estuarine species. The marine mammals of the world of Pangea, undivided, would be a particularly interesting fauna. In our world, marine mammals have evolved independently from 3 different terrestrial lineages. The cetaceans, whales, and dolphins evolved from land-dwelling artiodactyls. The pinnipeds, seals, sea lions, and walruses evolved from terrestrial carnivores, and the sirenians, manatees, and dugongs evolved from relatives of the elephants. This independent evolution is partly a consequence of the geographic isolation of the continents, which gave different lineages on different continents the opportunity to colonize the marine environment independently. In Pangea, undivided, the transition from land to sea, the remarkable evolutionary feat that produced whales and seals in our world, would also occur, because the ocean is an abundant and relatively unexploited resource from the terrestrial perspective. But in the connected world of the supercontinent, it would likely occur fewer times, because the successful marine mammal lineages that evolved would be able to spread around the entire coastline of the supercontinent, preempting the independent evolution of marine mammals elsewhere. The world of Pangea undivided might have one or two lineages of marine mammals, rather than the three independent lineages of our world. But those one or two lineages might be more diverse within themselves, more species, more ecological variety, filling more marine niches. The evolution of intelligence on a single continent, perhaps the most thought-provoking question about the world of Pangea undivided, is the question of intelligence. In our world, complex intelligence, the kind of intelligence associated with problem-solving, tool use, language, abstract thought, and the manipulation of the environment has evolved in several lineages independently, in the primates, including humans, in the corvids, crows and ravens, in the parrots, in the cetaceans, dolphins and whales, and to a lesser degree in the elephants and octopuses. This independent evolution of intelligence in multiple lineages is evidence that intelligence is, in some sense, a natural outcome of complex ecological interactions, that the pressures of competition, predation, and resource variability tend to favor cognitive flexibility, and that cognitive flexibility, given enough time and the right ecological context, tends to evolve toward what we call intelligence. In Pangea undivided, the evolution of intelligence would be shaped by the specific ecological pressures of the supercontinent, the vast distances of the interior, the extreme seasonality of the climate, the complexity of the monsoon cycles, and the migration patterns they drove, the competition within and between species in an environment where geographic isolation did not provide the refuge of separate evolutionary arenas. All of these might be expected to generate strong selective pressure for cognitive flexibility and problem-solving ability. Would intelligence evolve to the level we know from humans? This is impossible to say with certainty, but the ecological pressures that drove the evolution of human intelligence, complex social environments, tool use, the tracking and prediction of the movements of prey animals across large landscapes, the need to remember and navigate complex spatial environments, would all be present and perhaps intensified in the world of Pangea undivided. The lineage that first achieved high intelligence on Pangea undivided would not necessarily be the primates. In our world, the primates happen to be the lineage that, for a combination of historical and ecological reasons, first achieved human-level intelligence. But there is nothing uniquely privileged about the primate lineage. In this respect, the corvids and the cetaceans demonstrate that high intelligence can evolve in very different body plans from the primate one. In Pangea undivided, the lineage that first achieved something like human-level intelligence might be completely different from anything we know. A group descended from some ancestral mammal lineage that, in our world, remained cognitively modest but in the world of Pangea, undivided, was pressed by ecological circumstance to develop increasingly sophisticated cognitive abilities over millions of years. This hypothetical intelligent species would be shaped by the world it lived in. It would be a migratory species. Almost certainly, the extreme seasonality of the Pangean climate would favor animals capable of long-distance migration, and intelligence is associated with the ability to plan and navigate. It would be a social species. Intelligence in the animal world is almost always associated with complex social structures, because the complexity of social relationships is itself a powerful driver of cognitive evolution. It would be a flexible generalist, capable of exploiting multiple food sources in different seasons, exactly the kind of ecological flexibility that seems to be associated with the evolution of high intelligence. Would it eventually build technology? Would it discover fire and tools, and eventually science and art and civilization? These questions go beyond what we can reasonably speculate about from the available evidence. But if the history of intelligence in our own world teaches us anything, it is that once a lineage begins moving along the trajectory of increasing cognitive complexity, the selective pressures that drive it tend to be self-reinforcing. Intelligence begets more intelligence, because the more intelligent individuals within a population are more successful, and the social complexity that high intelligence enables creates new challenges that further favor increasing intelligence. Whether this trajectory on Pangea, undivided, would lead to something like civilization, and what that civilization might look like on a world without separate nations, without the geographical barriers that produced the cultural diversity of our own human history, is one of the most fascinating speculative questions we can ask. The human story on an unbroken earth. Let us assume, as a thought experiment within a thought experiment, that a species of human-level intelligence evolved on Pangea undivided, roughly comparable in its cognitive abilities and its social complexity to Homo sapiens. What would the human story, the story of a technological, cultural, conscious species, look like on an unbroken supercontinent? The most immediately obvious difference is the absence of separate cultures. In our world, the isolation of the continents produced an extraordinary diversity of human cultures, languages, religions, artistic traditions, and ways of understanding the world. The cultures of sub-Saharan Africa, of East Asia, of the Americas, of Oceania, of Europe, they are each unique, each the product of thousands of years of development in geographic isolation, each a different answer to the same fundamental human questions. This cultural diversity is one of the greatest treasures of our world, and it is a direct consequence of the separation of the continents. In Pangea undivided, there would be no such separation. The intelligent species would have spread across the supercontinent as a single, connected population. Languages would have developed, as they always do, but without the oceanic barriers that prevented contact between distant populations. The linguistic divergence would have been less extreme. Over long distances, communication would have been impeded by the sheer size of the continent and by the deserts and mountains and rivers that interrupted travel but not prevented. Languages would have spread and diversified, but they would have remained in contact with each other, borrowing words and structures and ideas across the enormous distances of the supercontinent. The development of technology on Pangea undivided would have been accelerated, paradoxically, by the connectivity of the supercontinent. In our world, the independent invention of key technologies in multiple separate cultures and the subsequent spread of those technologies across the globe has been one of the engines of human progress. fire, agriculture, metallurgy, writing, the wheel, the compass. All of these were invented multiple times, independently, in different parts of the world, and spread from their points of origin to other cultures through trade and conquest and migration. In Pangea undivided, with a connected global population, a technology invented anywhere could spread quickly to everywhere. The rate of technological accumulation would be higher, but the diversity of independent invention might be lower. In our world, the fact that the same problem was solved independently in China and in the Middle East and in Mesoamerica means that we have multiple independent perspectives on the problem and its solution, multiple cultural frameworks for understanding fire or agriculture or mathematics. In Pangea undivided, there might be only one solution to each problem, the one that first arose and spread before alternative solutions could develop. The technological world of Pangea undivided might be more homogeneous, more powerful in its internal consistency, perhaps, but less rich in its variety. The agricultural revolution on Pangea undivided would have been different in its timing and its geography. Agriculture in our world developed independently in multiple regions: the Fertile Crescent, China, Mesoamerica, New Guinea, the Sahel, and each of these independent inventions was based on the specific plants and animals available in each region. The Fertile Crescent had wheat and barley and sheep and goats. China had rice and millet and pigs. Mesoamerica had maize and beans and squash. These different agricultural packages produced different foods, different agricultural technologies, different economic systems, and eventually different civilizations. In Pangea undivided, the agricultural revolution would have been centered in whichever region of the supercontinent had the most favorable combination of climate and domesticable plants and animals, probably somewhere on the monsoon coasts, where seasonal flooding and draining created productive floodplains similar to those of the Fertile Crescent and the Nile and the Yangtze and the Indus. The specific crops and animals domesticated would depend on what was available in that region. Once developed, the agricultural technology would spread relatively quickly across the supercontinent because the connected land surface would not present the absolute barriers to diffusion that the oceans did in our world. The civilization of Pangea undivided, if it developed, would be a civilization without the concept of the known world as a bounded thing. In our world, every human civilization has had a sense of its own territory and the unknown territory beyond the barbarians at the edge of the map, the ocean horizon, the distant land that might or might not exist. This sense of the bounded known world and the unknowable beyond has been enormously productive, driving exploration and conquest and trade and the imagination of what lies beyond the horizon. In Pangea undivided, the horizon is always the same continent. There is no ocean to cross, no new world to discover, or rather, the new world is always just more of the same world, more of the same supercontinent, more mountains and rivers and deserts and plains that are continuous with the ones you already know. The impulse toward exploration would still exist. The supercontinent is vast, and much of it is unexplored, but the discovery of a new continent, the shock of encounter with peoples who have developed in complete isolation for thousands of years, the radical reimagining of the world that comes with discovering that the world is larger and more varied than you thought. None of that would happen in the same way on Pangea undivided. The diseases of a connected world, one of the less celebrated but most consequential aspects of the world of Pangea undivided, would be its disease ecology. The history of disease in our world is intimately connected to the history of the continents, to the isolation that allowed diseases to develop in one population, and then, when the isolation was broken by human migration or conquest, to devastate populations that had no prior exposure and therefore no immunity. The most dramatic example in human history is the Columbian Exchange, the transfer of diseases between the Old World and the Americas that followed Columbus's arrival in 1492. The peoples of the Americas, isolated from the Old World for tens of thousands of years, had no exposure to the major epidemic diseases of the Eurasian world: smallpox, measles, influenza, bubonic plague, typhus, cholera. When European explorers and settlers arrived, they brought these diseases with them, and the resulting epidemics were catastrophic. Estimates of the mortality vary, but the broad consensus is that within a century of European contact, the indigenous populations of the Americas declined by 50 to 90%, tens of millions of people, perhaps more, killed not primarily by European weapons, but by European diseases. This catastrophe was a consequence of isolation, of the fact that the Americas had been separated from Eurasia for long enough that the disease environments of the two worlds had diverged completely. In the Old World, populations had been exposed to these diseases for thousands of years, long enough for natural selection to produce some degree of genetic resistance in survivors, and long enough for cultural adaptations, quarantine, treatment practices, the avoidance of infected individuals to develop. In the Americas, neither genetic nor cultural adaptation had occurred because the diseases were not present. In the world of Pangea undivided, this kind of catastrophic disease encounter would not happen because there would be no isolated continental populations. The diseases of the supercontinent would be shared diseases, pathogens that had spread across the connected landmass and to which all populations had been exposed. The disease ecology of Pangea undivided would be a single global disease ecology, not the collection of separate regional ecologies that characterized our world before the age of exploration. This would have advantages and disadvantages. The advantage is that there would be no Columbian Exchange disasters, no moment when the meeting of previously isolated populations unleashed diseases for which one population had no defense. The disease ecology of Pangea undivided would be more uniform, more stable, more in equilibrium with its host populations. The disadvantage is that the diseases of Pangea undivided would be, in some sense, more pervasive. In our world, geographic isolation has sometimes protected populations from diseases that were widespread elsewhere. Island populations, in particular, often had disease environments that were simpler and less burdensome than those of continental populations, precisely because the ocean barrier kept many pathogens out. In Pangea undivided, no such refuge would exist. The diseases that spread across the supercontinent would reach every population, everywhere, because there is nowhere to hide on a continent that has no ocean boundaries. The zoonotic diseases, the diseases that jump from animal hosts to human hosts, would be particularly significant in the disease ecology of Pangea undivided. In our world, many of the most important infectious diseases are zoonoses. Influenza comes from birds and pigs, HIV from chimpanzees, Ebola from bats, SARS from bats via civets, COVID-19 from bats via an intermediate host. The diversity of animal species across the supercontinent and the dense ecological interactions between the intelligent species and the animal fauna of Pangea undivided would create many opportunities for zoonotic spillover. The resources of the supercontinent. The resources of Pangea undivided, the mineral resources, the energy resources, the water resources would be distributed differently from those of the modern world, and their accessibility and their exploitation would be shaped by the specific geography of the supercontinent. The coal, oil, and natural gas of the modern world are products of specific geological processes that occurred at specific times and places in the history of the separate continents. The Carboniferous coal measures of Europe and North America are the compressed remains of the swamp forests that covered the equatorial regions of Pangea during the Carboniferous period. The oil fields of the Middle East are the remains of marine organisms that lived in the Tethys Sea during the Cretaceous. The coal fields of Australia are from the Permian forests of Gondwana. In the world of Pangea undivided, these resources would still exist, but they would be concentrated in different areas because the geology that produced them would be different. The fossil fuel resources of Pangea undivided would be the product of 200 million years of geological processes on an unrifted continent, different from our world in their specific locations and extents, but comparable in their total quantity, because the total amount of organic matter buried in the Earth's crust is determined by the total productivity of the biosphere over geological time. The mineral resources of Pangea undivided would also be different in distribution. Many important mineral deposits in the modern world are found in rocks that were formed at the margins of the ancient continents, at the sites of ancient subduction zones, ancient volcanic arcs, ancient ocean ridges. In Pangea undivided, the history of subduction and volcanic activity would be focused at the margins of the supercontinent, the coastlines facing the Panthalassa, rather than distributed across multiple continental interiors as in our world. The richest mineral deposits of Pangea undivided would tend to be concentrated in the coastal mountain ranges, where subduction-related volcanism had been active for hundreds of millions of years. The water resources of Pangea undivided would be severely constrained in the interior. The vast interior desert, with its almost non-existent precipitation and its deep, dry sediments, would have very little fresh water. The great rivers that drained the monsoon coasts would carry fresh water deep into the interior before losing it to evaporation, but they would not carry enough to make the interior habitable in the modern sense. The groundwater resources of the interior would be limited, unlike the Great Plains of North America, where the Ogallala Aquifer stores enormous quantities of ancient water that can be pumped for irrigation. The desert interior of Pangea undivided would have groundwater only in specific geological contexts. The ocean resources, fish, shellfish, seaweed, sea salt, the mineral resources of the continental shelves would be abundant along the coastlines of the supercontinent. The Panthalassa, cold and productive along the western margin and warm and clear along the eastern margin and in the tropics, would support rich fisheries. The continental shelves, wherever they existed along the margins of Pangea undivided, would be rich in the same resources that continental shelves are rich in today. A day on Pangea undivided. Let us spend a day on Pangea undivided. A slow day, a quiet day, a day in which we simply inhabit the world and let its character wash over us the way the best sleep does, not analyzing, not cataloging, but experiencing. We are on the eastern coast of the supercontinent, the coast that faces the warm, sheltered waters of the ancient Tethys or its successor, the shallow inland sea that has replaced it in the 200 million years since the Triassic. The sky is lightening in the east, over the sea. The horizon is flat and clean and distant, and the first colors of dawn are violet and rose, and the pale gold that comes just before the actual sunrise. The air smells of the sea and of wet vegetation. The coastal forests here are dense, driven by the reliable moisture of the eastern coast and the warmth of the tropical latitude. The forest is unlike any forest, you know. The trees are tall, many of them, but their shapes are unfamiliar, not the shapes of oaks or beeches or tropical palms, but something different. Something evolved over a different 200 million years from the survivors of the Permian extinction. Their leaves are large and dark and waxy, adapted to the intense monsoon rains that fall here for 5 months of the year. Their trunks are massive, buttressed at the base where the thin tropical soil cannot anchor them otherwise. The sounds of the morning are the sounds of birds, many birds, of species you have never heard or seen, calling from the canopy and the understory in voices that are recognizable as bird voices, but strange in their specific patterns. Calls evolved over millions of years in this forest, from ancestors who would be familiar, but whose descendants are not. Some calls are rich and melodic, some are harsh and metallic, some are the thin, high whistles of small birds defining territory. Beneath them, the constant, complex background of insect sound the stridulation of creatures that have no names in any language you know. The sun rises. Where it touches the forest canopy, the leaves glow briefly with transmitted light, a vivid, almost painful green. The temperature rises quickly, as it does in the tropics, and by mid-morning, the air is hot and humid. The birds go quiet in the middle heat, retreating to the shadow of the canopy. The insects take over louder, more insistent, the cicada-like creatures creating a wall of sound that is somehow both numbing and beautiful. In the forest, midday, the light is dimmed by the canopy to a green, filtered glow. The air is still and wet and smells of decomposing leaves and fungus and flowers. Something large moves through the understory 100 meters away, something big, its passage marked by the cracking of branches and the startled flight of birds. A herbivore of some kind, something that browses the lower branches of the forest, something we have no name for. It does not see us or does not care. It moves on. In the afternoon, the sky builds. The trade winds coming off the warm inland sea have been feeding moisture into the atmosphere all morning, and by mid-afternoon, the cumulus clouds have built to cumulonimbus the great, vertical, anvil-topped storm clouds that bring the daily tropical rainfall. The light takes on a peculiar greenish quality that anyone who has spent time in the tropics recognizes instantly, the light of an incoming storm. The air cools slightly, the birds go quiet, and then the rain begins. It is not a gentle rain. It is the tropical monsoon rain, the kind that makes conversation impossible at 3 meters, the kind that turns paths into streams and streams into rivers in minutes. The forest accepts it with the equanimity of long experience, the leaves channeling the water to the ground, the root systems drinking it in, the streams running full and brown. After an hour, the rain eases, and by evening the sky is clear again, washed and brilliant, the sun setting over the interior of the continent in a blaze of orange and red. Night comes quickly in the tropics. The stars appear clear and numerous, because the air has been washed clean by the afternoon rain, and because there is no light pollution here, no city glow on the horizon, nothing but the star-filled sky of a living world. The Milky Way is extraordinary, a dense band of light arching from horizon to horizon, so bright that it casts faint shadows. Something calls from the darkness of the forest, a long, haunting sound, repeated at intervals, the territorial call of a nocturnal predator we have no name for. The warmth of the day persists into the night here on the eastern coast. The inland sea nearby keeps the temperature from falling too far. You could sleep outside on the warm ground and wake to find the air barely cooler than it was at dusk. The forest never goes entirely quiet. The night shift of insects and nocturnal animals is as active as the day shift, just differently composed, differently voiced. The world of Pangea undivided does not sleep. It is always alive, somewhere, in some form, in some register of existence. What we would have lost, the world of Pangea undivided would be, in many ways, a poorer world than the one we know poorer, specifically in the quality and the depth and the range of its biological diversity. We would have lost the extraordinary divergence of the marsupials, the kangaroo and the koala and the wombat and the Tasmanian devil and the quokka creatures that represent a completely independent evolutionary solution to the challenges of large-bodied mammalian life, a solution that has been developing in isolation for 45 million years, would not exist. There would be no platypi, no echidnas, the only surviving egg-laying mammals. These ancient lineages, with their unique physiologies and behaviors, are irreplaceable. They are nature's answer to a question that was only possible because Australia was isolated. In Pangea undivided, the question was never asked in isolation, and so the answer was never forced. We would have lost the extraordinary biodiversity of the Amazon rainforest, the Congo Basin, the forests of Southeast Asia, the coral reefs of the Indo-Pacific. All of these are products of long evolutionary history in regions that were, to varying degrees, isolated or semi-isolated by the geographic barriers produced by the breakup of Pangea. The tree of life has branches only because there were geographic barriers that allowed those branches to grow independently. In Pangea undivided, with fewer barriers, the tree would have fewer branches. We would have lost the extraordinary cultural diversity of the human world, the diversity of languages and religions, and artistic traditions, and ways of being human, that is itself a product of the geographic separation that allowed human populations to develop in relative isolation. The linguistic diversity of the world, with its 7,000 languages, its dozens of language families, its extraordinary variety of phonological and grammatical systems, is a direct reflection of the geographic isolation of human populations over tens of thousands of years. In Pangea undivided, this diversity would be greatly reduced. We would have lost the specific geography of our world, the Mediterranean Sea, and the English Channel, and the Caribbean, and the Indian Ocean, and the Pacific, all the bodies of water that have shaped human history, that have been crossed and explored and fought over, that have served as barriers and as highways, and as sources of food and trade and cultural exchange. The specific geography of our world is inseparable from the specific history of our world, and in Pangea undivided, both would be different beyond recognition, what we would have gained, but the world of Pangea undivided would not only be a world of losses, it would also be a world of extraordinary gains, things that exist in that world, but not in ours, possibilities that the connected supercontinent enables, that the separated continents of our world cannot. We would have gained the ability to walk everywhere, the simple, profound, almost almost incomprehensible fact of being able to walk without crossing an ocean, without a ship or a plane, from any point on Earth to any other point. The freedom of the connected world, the freedom of a planet without the barriers of deep water, would be a form of freedom that no human being in our world has ever experienced. You could, in principle, walk to the opposite side of the planet. It would take years. It would be an epic journey through desert and mountain and forest and tundra. But you could do it. The land would be continuous. The path, however difficult, would be there. We would have gained a more uniform global culture, not a monoculture, not a bland sameness, but a culture that has developed over long contact and exchange rather than long isolation. The richness of that culture would be different from the richness of our cultural diversity. It would be the richness of depth rather than the richness of divergence. A world where ideas and technologies and art forms and philosophies have been in contact and dialogue for the entire span of human history, rather than developing separately and encountering each other only in the last few centuries. We would have gained the megafauna of the connected world, the great animals that might have evolved on the continuous supercontinent, the giants of a world without oceanic barriers. We would have gained the evolutionary experiments of 200 million years of life on a single landmass, forms and lineages and ecological relationships that we cannot even imagine because they require a history that is not ours. We would have gained a different kind of science, a science that developed in response to the specific questions raised by life on a supercontinent, a geology that studied the dynamics of a world without ocean basins, a biology that grappled with the evolutionary patterns of a connected biosphere rather than the separated biotas of our world. The science of Pangea undivided might have been more unified, more global in its perspective, less bedeviled by the parochialism that has sometimes characterized the science of separate cultures encountering each other's work for the first time. Epilogue. The gift of separation. The earth broke apart. In our world, in the actual history of the actual planet, the forces that pulled Pangea apart were stronger than the forces that might have held it together, and the supercontinent that had endured for 160 million years began 175 million years ago to fracture, slowly, at the speed of fingernail growth. The continents drifted to where they are today. The Atlantic opened, the Indian Ocean opened, the Drake Passage opened between South America and Antarctica, and the cold Southern Ocean began to circulate around the Antarctic continent, cooling it and eventually glaciating it. The world we know was assembled, piece by piece, over 175 million years of continental drift. And from that separation from the rifts and the drifts and the new oceans and the isolated continents came everything that makes our world what it is. The biological diversity that fills every ecosystem on the planet. The extraordinary variety of human cultures and languages and ways of being. The specific geography that has shaped every civilization, every trade route, every war, every migration, every act of exploration and discovery and encounter. The breakup of Pangea was not a loss. It was a gift, the gift of separation, the gift of difference, the gift of a world that has been pulled apart and put back together in new ways, in which the putting apart created possibilities that the original unity could never have imagined. Lying here, in the dark, you are on a fragment of the old supercontinent. The ground beneath your house is a piece of a puzzle that was once joined to pieces now in different parts of the world. The rocks of your region were once adjacent to rocks that are now in Africa, or Australia, or Antarctica. The sediments that underlie your city were deposited in a world that looked nothing like the world you know. The separation gave you the ocean you dream of, and the mountains you love, and the diversity of life that surrounds you, and the cultural richness of the human world that produced the language you think in, and the art you respond to, and the food you eat, and the ideas that animate your waking hours. All of it was made possible, ultimately, by the breakup of a supercontinent 175 million years ago. Pangea was one. It was extraordinary in its unity, in its vast single-continent scale, in the gigantic simplicity of its geography. But its breaking made our world. Its fragmentation produced the conditions in which life diverged, and cultures diverged, and the astonishing variety of the living world. The kangaroos and the Amazon, and the coral reefs, and the 10,000 languages and the Himalayas, and the Mediterranean and the Pacific came into being. The world of Pangea undivided would have its own extraordinary qualities. We have explored them tonight: the vast interior desert, the monstrous monsoons, the world ocean, the giant animals of the connected plains, the unified humanity of a species that never had to cross water to meet itself. It would be a real world, a full world, a world worthy of contemplation and wonder. But it is not our world. Our world came from the fracture, from the slow drift, from the patient accumulation of oceanic distance between lands that had once touched. Our world is a world of pieces, and the diversity of the pieces is its greatest treasure. So, rest now. The continents have found their places. For this moment in geological time, they will continue to drift. The Atlantic is still widening. Australia is still moving northward. The Pacific is slowly shrinking. The Mediterranean is destined to close in tens of millions of years as Africa continues to press northward into Europe. The Earth is still Pangea, in a sense still one planet, one rock, one connected system of mantle and crust and ocean and atmosphere. But its surface is arranged in the specific way that produced you, and the specific place where you are lying, and the specific combination of circumstances that made your existence possible. The supercontinent is in the past, the separated world is in the present, and the present, tonight, is warm and dark and quiet, and you are safely in it, a child of the rifts, an inheritor of the drift, a living being on a planet that broke itself apart in order to become, eventually, the extraordinary, diverse, beautiful world that holds you now. Sleep well. Good night.